Hey, good morning. Glad to see a few of you could join me for the live stream. That's always appreciated. Week 13. So, getting really short on time these days. Uh, yeah, so the labs last week, they all look solid. Every person who submitted one got 100%, which um, I kind of feel like I'm throwing this out onto ears that aren't going to hear it. So probably if you're here or watching the video later, you don't need to hear any of this. But hello again, Robo. Nice to see you again. Thanks for spending the long morning listening to me talk. So if you know people who are struggling or have fallen behind, um, there's not a whole lot I can do out here in the world of an online course other than offer channels to communicate with me. And I never get inbox messages. I never get requests for office hours. Um, and I do see some, but maybe we need to see more piazza messaging for people to get help. So if you know people who are struggling, just remind them, ask them, have you taken advantage of all the different ways you can get help? I know some people aren't comfortable meeting one-on-one with an instructor, but people just need to ask themselves, like, which is more important, succeeding in the class or feeling uncomfortable around me for a while. Anyway, that's all I can say about that. The ones who submitted work, though, it looks great. So just keep plugging along like you're doing. And if you can help me get the word out to people that they can and should get help where they need it, I'd appreciate that. Okay, so we are finally, we started to kind of do what I would consider to be, the core of computer science when we started with linked lists. Because we're finally starting to do difficult algorithms that require complex coding effort and kind of an understanding of dynamic memory and C++ pointer syntax, and then how to generate a picture of an abstract structure in your head that doesn't look anything like what the code looks like. Good morning, Magenta. Sorry if I let you sit there on that comment for a while. Nice to see you. So yes, these things are hard that we're doing. Computer science is challenging because we deal in abstract ideas that we then have to translate into algorithms in our class in the C++ language, which is hard enough by itself without having also then to use it to express complex algorithms that are trying to turn an abstract idea into reality in software. So none of that is easy. It takes lots and lots of practice. The syntax takes practice. The algorithms take practice. The generating an image in your head and the different techniques that you have to assist yourself with that. Drawing pictures is what I like. That all takes practice. So unfortunately, I don't know of any easy way around any of that. If someone were to come up with the easy way around it, we probably wouldn't need programmers anymore because we could just code in the easy way around it into a computer. Okay, so Ember Wolf. Good morning, Ember Wolf. But Ember Wolf says in chat that they've been drawing lots of pictures. So that's great because it takes practice to draw pictures as well. To kind of figure out the style and kind of what the images in your own pictures need to be to help you understand, which is why practice is so important because you can then develop your preferences. So what we're adding this week is recursive algorithms. It's a completely different way of thinking, doing recursion. Good morning, Tony. Nice to see you. So you'll notice that I put a big bar on the agenda down there, and that's because the first part of the class, the new content, is all about recursive thinking and recursive algorithms. And then I'll put a break in the video, and then we will continue with prepping ourselves for project number 3, which is now due on this coming Sunday. So got a bunch of the algorithms, at least parts of and implementations, or at least parts of implementations of, and then ideas for others. So that's why the bar is there, because it's going to be a pretty big shift from one part of the class to the other. Okay, so recursion. Recursion is not suitable for solving every kind of problem. And I have created some problems in your lab this week that are a little bit artificial. They're not even necessarily best solved with recursion. But we're coming up after project 3 is due and we start on project 4 stuff. We need to know how to think recursively to deal with the complexities of that data structure. So what we're doing this week is kind of getting our brains warmed up to the idea of recursion. What is it? What does it look like in code? How do we set up a proper recursive algorithm? But doing a recursive algorithm by yourself, sort of in a blue sky environment, meaning there's nothing already there, is hard. It's just another one of those things that takes practice. So we'll talk about it. I will talk about sort of technically how it works, which helps some people, I think. And then we'll look around the lab work for this week and see where I can offer you some tips to help you solve it. So I'm just kind of telling you all, that's a lot of words to say. I understand that recursive thinking is difficult. It's one of the most difficult things to do in computer science. You're going to get a lot of practice at it in the coming weeks, but getting comfortable with it is its own problem. So you'll come to recognize a recursive algorithm. You'll come to recognize kind of what's important in terms of creating a recursive algorithm. Figuring out the situations where a recursive algorithm makes sense is more difficult, but I will be giving you several situations where recursion is really the only and best technique to do it. So that's how you're going to get exposed to when is this a suitable way of solving a particular problem. Okay, I'm going to start by creating one of the classics in Replit. Actually, maybe I should walk through the module first. And then I'll do one of the classic recursive algorithms that you're going to see over and over and over again when you do the reading. Okay, so here we are. We are in week of November 14th, the 13th week. The new idea is recursion. That is in preparation for what we're going to use a great deal of on the 4th project. But the reason why we're kind of getting into project 4 stuff is because I allowed a little bit more time for some of the earlier projects. Like this first project, probably that's more time than was needed. But that means that we're kind of, as we're finishing now project 3 this week, we're also starting to build up our toolkit for project 4. So, okay, so project 3 due this Sunday. Let me go look at week 13. And then I will bring up Replit and implement one of the classic ones. All right, so it's really thinking recursively that's the big deal here. And this week is mostly about just getting accustomed to the idea of recursive thinking and viewing some recursive algorithms and developing some recursive solutions. You see recursion all the time in the world. You just don't think about it as being recursion. I'll talk about that as well. So these two readings, they both have some of the classic kind of how we introduce people in computer science to recursion code in them and algorithms in them. So you'll get to see lots of repeats on that stuff. Yeah, good one. So Magenta says like the Fibonacci sequence. Yes. So Magenta's exactly right in chat that the Fibonacci sequence is one of the classic problems that we use to introduce people to recursive thinking. But the way I tend to think of it is that any problem that kind of seems to break itself down into smaller and smaller steps until you get to kind of an irreducible step, that's when recursion can be useful. C++ doesn't drive a lot of recursive thinking. There are languages and programming styles where recursive thinking is a lot more important. So F#, OCaml, Erlang, Elixir, those are big ones where recursive. So there are languages that kind of encourage more recursive thinking and recursive solutions, but it is useful for certain kinds of problems, even in C++. But good one, Magenta, that you know that Fibonacci is one of the classics. That's another one. So Magenta points out that fractals is also a recursive algorithm. That's true. Fractals are recursive. They are basically they create complexity by kind of repeating themselves on top of themselves over and over and over again. Mother Nature does this a lot too, by the way. If you look at any tree, and you look at the structure of the branches, and if you look at a leaf on a tree and you look at the structure of the veins in the leaf, you can kind of see where Mother Nature is using a recursive algorithm to generate complexity from smaller building blocks. So fractals and Mother Nature are kind of recursion going outward. Start with something simple and repeat upon itself as you go kind of out to greater complexity. For us, we're often going to use recursion to start at greater complexity and whittle ourselves down to some irreducible moment. Yes, that's true. Mother Nature on the micro and the macro scale uses a great deal of recursion. Oh, shoot. Sorry, I slipped tabs before. So did I look at things? Oh, yeah, I did. Okay, so lab. Let me get that up so that I can come back to it here in a moment. It's a relatively small lab, but because it's recursion, it takes some thought. So discussion this week is meant to be a little bit of a break, although if you can help each other out in the discussion, it's about just cheerleading ourselves for Project 3, but it's also a good place if you've come across something that you thought was kind of a big moment for you in Project 3, like, oh, once I kind of figured this thing out, it made my life so much easier. That would be good stuff to share in discussion. But Project 3 discussion this week doesn't require research, just getting in there and kind of sharing an encouragement and good practices or good ideas if you have them. And reminders, lab is always, discussion is always, project due on Sunday. So next week, we will have a lab as usual. We will have a discussion as usual. We will have a live stream as usual. So if you are doing anything around Thanksgiving, just please plan accordingly. Remember, you do get 2 free drops. So your lowest 2 labs and your lowest 2 discussions are automatically dropped in Canvas by Canvas, the way I set it up. So if you just decide next week has gotten too chaotic, you always have that fallback with no consequence on your grade. Okay, so let's go into Replit and let's do one of the classic ones. And we might as well do Fibonacci as well while we're at it. So I'll put some notes in here. So a recursive algorithm or function calls itself. So one of the interesting things about recursion is that when you develop these algorithms, you develop them to solve themselves by calling themselves, which is kind of weird. But a classic one is factorial. Problem that can be solved recursively. And probably you even learned this in a math class. So if you get something like 5 factorial, which is 5 times 4 times 3 times 2 times 1, you kind of recognize that there's a pattern in here. And it turns out that you can express this kind of as a descending series of smaller parts of itself. So now we're going sort of from the big thing, 5 factorial, down to the irreducible thing. So what does that look like? Well, 5 factorial is really 5 times 4 factorial, if you think about it. So it can be solved by sort of relying upon its own solution or its own, I guess I'd say solution, algorithm down to some irreducible point. Anyway, so another way of saying 5 factorial is that it is 5 times 4 factorial. Another way of saying that is 5 times 4 times 3 factorial. And you notice here at every step, 4 factorial, well, that's the same calculation as 5 factorial, 4 factorial, 3 factorial, 2 factorial, times 1 factorial, which is really 5 times 4 times 3 times 2 times 1. It's back to where we started. So that it can be solved recursively is when you recognize that the solution can be derived by kind of whittling yourself down to this irreducible point. The irreducible point, by the way, is 1 factorial. There's no sense in going any deeper than 1 factorial because you can't get anything else. All right, so everyone I think has probably seen that. What is 5 factorial? Well, it's really the same as saying 5 times 4 factorial, which, by the way, is really saying 5 times 5 minus 1 factorial. So I'm not going to keep going with this, but maybe you get the idea. Do you see how we can also kind of conceive of 5 factorial as being the same as saying 5 times 1 less than 5 factorial? And 5 less than 1 less than 5 factorial is the same as 1 less than 5 times 1 less than 5 less than 1 less than 1 less than 5 factorial. Good morning, EdCast. Nice to see you. So again, what we're trying to do is just warm up our brains to the concept of a recursive algorithm. So I begin to notice that I don't even need the other values other than really 5 and 1 here to express the solution. It's just something less 1, something less 1, something less 1. And when it comes down to it, I can rewrite the whole thing as n factorial equals n times n minus 1 factorial. That's an algorithm. And if I apply that all the way down until I get to 1, I get the solution. So what does this look like in code? So we have int the factorial of some int n. So if we write this as a function, we'll call it factorial. To compute the factorial of n is really saying, well, what I really need to return is n times the factorial of n less 1. So that's literally the whole solution. What is impossible to see in this is how that could possibly be working. Here is the indicator that I have a recursive function, which means that I have a recursive algorithm and that the function calls itself. So I'm actually going to run this. I don't recommend you do this because there's something terribly wrong with it. But this is the basic algorithm for factorial. It is that number times the factorial of 1 less than itself. Now I'm going to run this. Let me get the using directive to allow this to happen. Okay, so that's the algorithm. I'm going to try to compute it and something terrible is going to happen. I do. So Ember Wolf, you are exactly right. I need something to bring this all to an end. So I'm going to do it wrong first, and then we'll do it right. While we're at it, why don't we say, why don't we just see what's happening here? All right, so don't you do this at home. I'm going to do it, and I'm going to use Control-C to kill it. So, yes, I do need something to stop the algorithm. And you'll notice when I did 5 factorial up here in the notes, I manually stopped when I got to 1. I knew there was no point in descending any further from that because I don't get the right answer anymore. At a point, I start to get something weird. So I manually stopped here. I'm not manually stopping here because I want to see what happens when I do it wrong. And you are right, Magenta. This is going to go on forever, so this is why I don't think you should do it, but I'm going to go ahead and do it. So here we go. Okay, so I'll stop it. It just kept going and going and going and going and going and going and going. And by the way, it never seemed to stop. So it just seems to go on forever and ever and ever and ever and ever. And in chat, both Emberwolf and Magenta noted that something's going to be wrong here. And in fact, when we ran it, we noticed that the algorithm never had a place to stop. So the whole trick, once you have recognized that you can use a recursive solution, one of the first things you should do is identify the irreducible moment. There is a moment in every recursive algorithm where you cannot go any further without causing a problem. With factorial, I'm going to go ahead and say less than or equal to 1. But whenever you're computing an n that is less than or equal to 1, you got to stop. We'll just assume that it's going to be 1, but you need to stop and return 1 because 1 factorial is 1. And if you don't stop somewhere, you're going to go into negatives and you're going to go forever. So yeah, Emberwolf asked, what happens if I don't stop somewhere? Will it crash? And the answer is yes, it will crash. Eventually the program will crash because the algorithm will burn up the available memory it has. So this is called, without this place to stop, it's called infinite recursion. So you don't want infinite recursion. It's like an infinite loop. It will never stop. And probably the program will ultimately crash with infinite recursion. So you need to find somewhere to stop the algorithm. Every recursive algorithm has a place where it must stop. For factorial, it must stop when you get to 1 or below it. Then you just need to spit out a 1. I'm going to do it this way, in fact. I'm going to spit out a result equals 1. Let's see, will it crash? Yes. So Magenta asks if one of the numbers is multiplied. If there's somewhere in 0. So no, 0 factorial probably equals 1. Now we can handle this problem partly. So we can take the negatives out simply by making these unsigned, and then the compiler can do some of the work for us. So if we make the n unsigned, then we don't have to worry about the negatives anymore, although we still have to worry about the going all the way around over and over. In fact, let me do that. So if we make them unsigned, we can't drop below 0, but watch what happens. So what happens actually when you get down to 0 with unsigned, it wraps back around to the top end of what an unsigned integer can be and then begins working its way. So you get in this endless loop of unsigned integers, down to 0, back to the highest value, down to 0, back to the highest value, over and over and over again. So making n unsigned takes care of the negative problem. It doesn't take care of the we got to stop somewhere problem. So every recursive algorithm has got to stop somewhere. So in the case of factorial, it is when we get to 1 or below, we're going to return a 1. Okay, so let's do, actually we don't need an else because the return would have happened. I'll go ahead and put an else just to not confuse people. The other thing to note here, and you'll hear me say this a lot when we start doing binary search trees, because this function returns an unsigned int, both the break case and the continue case have to return something. For this to work, you have to return something in the if and the else. So when the n is less than or equal to 1, I'm going to return a 1. Everything else, I'm going to return the result of multiplying the n times the factorial of 1 less than the n. I'm also going to print out the result so we can see how this unravels. Oh yeah, I'm going to have to say, let's see, how do I show this to you? Yeah. All right, so I put these output statements here so that we can see the thing happen in real time. So we can see what does the computer actually do with this. Let's see if that's the output that I want. No, it's not really what I want. I want times let's see if that works out. Times n. I think this will work. So I'm doing this just so we can see the thing before I draw pictures of it. So the thing to note here is that I didn't put a space after this. Okay, so I want you to see what happens though. When I call 5 factorial, what happens? It actually calls 4 factorial, which calls 3 factorial. Notice no solutions are being produced yet, which calls 2 factorial, which calls 1 factorial. And then at that point, notice everything starts to unravel because 1 factorial causes a 1 to drop, which allows the factorial of 2, which is 2 times the factorial of 1 to drop, which allows the 2 times 1, which is 2 times 3 to drop. 2 times 3 is 6, times 4 is 24, times the original 5 is 120. So it literally kind of stacks up and then unravels itself. I'm going to draw a picture of this. So this is what I wanted to show you the work that the computer had to do to compute 5 factorial is actually have 5 calls to this function which don't begin to unravel themselves until we hit that irreducible moment, that stop or break case, as I call it. So pretty funky. So I'm going to show you kind of how this works on the technical side, and that helps some people, but not all people. So this is a messy factorial because I wanted it to be understandable when we ran it. The better one, which I will then comment out, would look like this. So factorial of an unsigned int n is if n is less than or equal to 1, turn n. So this is the clean one. Because the if does a return, we don't need an else actually because we can't get to this other statement if the if happens. So sometimes you can throw out the else part because you don't need it because the if part is already causing the function to end. So this is the clean and neat one. This is the one that we can use to study a recursive algorithm, so it will print for us what's happening in what order. Okay, switching over to terrible pictures for a moment. Okay, so what happens when I call 5 factorial? What happens is that the function factorial 5 is called and these are called stack frames technically. I mean, the technical terminology for this is a stack frame. A frame is one execution of the function. The stack part you're going to see in just a moment. So when I call 5 factorial, I get a stack frame, which is one instance of the function running. Now the problem here is that this call to this function requires another call to this function, and it can't actually wait until 4 factorial has been completely computed. So what happens when we call factorial of n minus 1 here? Another stack frame is created. And the reason why this is useful, at least in my mind, to see this and to know this is happening, the stack frames on the bottom can't release their results until the stack frames above them have done so. So right now, the factorial 5 stack frame does not have an answer to this question. What is 4 factorial? It doesn't know until 4 factorial produces a result that can be plugged in here. Okay, so now I'm in this stack frame, a frame being one execution of the function, stacked the most recent call on top of the last call. So the one on the bottom is stuck here until the one above it goes away. Now this one is going to cause another stack frame to happen. Which is factorial 3, which is 3 times 2 factorial. So now the 5 has to wait on the 4, and the 4 has to wait on the 3 factorial stack frame. What happens on the 3 factorial? Darn it, we don't have an answer to this question because 2 factorial is going to be called to compute it. So now the 5 stack frame, which was actually the first one to be created, can't go anywhere until the 4 factorial 4 stack frame goes away, which it hasn't yet because it can't go away until the factorial 3 stack frame goes away. It can't because it's underneath the 2 factorial stack frame, which doesn't have an answer yet because it's waiting on factorial 1 stack frame, which finally, thankfully, we get an answer. So as soon as we get to an answer, return 1 here, the stack frames can begin to unravel themselves, just like we saw in Replit in my little output. So this one actually returns an answer. So we can plug in the answer here and then scrub this stack frame. It pops off. And now the 2, which has its answer, can proceed. 2 times 1 is 2, which means it can deliver its answer and go away. So now factorial 3 has the answer it was waiting for. It can produce its result, which is 6, and then go away. Now factorial 4 can produce the answer that it was supposed to produce, 24. It can go away. And now finally, factorial 5 has the answer it was waiting for, so it can produce the final result. Now the stack is completely clear to frames because the function has returned. Now for me, this helped to understand kind of that this is how they function. It helped me to understand how these algorithms work better. Doesn't for everybody, but for some people it does. This place where the stack stops is a big deal. If you never get to a place where the stack just says I'm done, then you will never get to the place where it can unravel itself. It'll just keep stacking up and up and up and up until there's no more memory to hold stack frames and the program crashes. So that's sort of the technicals of how a recursive function executes on the system, at least in C++. So anyway, that may or may not help some people. If it does, I'm glad for that. That's how they execute. Okay, so yeah, we'll do another one. So let me switch views. I'm not going to do Fibonacci. You'll see that in your reading, and I recommend that you go try it out. I can tell you that one of my humbling computer science school moments was this factorial function right here, which I thought I had nailed down, and I went into an exam and I thought, oh, that's easy. I don't even need to study it. It's so simple. And I couldn't come up with it. It was one of my more humbling moments, I thought, because it just seemed so simple. And like, how could I not remember this? But I couldn't. I had to actually kind of force myself to learn how it works to be able to remember how to write one. So your mileage may be different. I'm just heads up. These are hard. Some of us find them harder than maybe other people find them, but they're hard. Okay, I'm going to do another one, and it's very closely related to what we're doing in lab this week. So I'm going to do kind of a, that's true. So Tony points out that sometimes those moments where you feel most humbled might be the ones where you are getting the best learning out of them. And I totally agree. So that was for me when I had that bad test moment and thought, oh, I own this, and I didn't. I redoubled my efforts to write recursive algorithms over and over and over again until I began to kind of learn not just what they're supposed to look like, but actually how they work. Okay. So let me think how I'm going to do this one. We'll start this way. Yeah. So I'm gonna do one with vectors, and the code's gonna look weird, but I want to do a recursive algorithm with vectors. So two things with a recursive algorithm: you have to have, what's the word I'm looking for? The stop case or the break case. You have to identify right early on what would be the situation where I need to stop doing this and let the algorithm unravel itself. That's the first thing. And the other thing is figuring out the appropriate way to call the function itself with some subset of the problem as you go from the bigger thing to whittle it down to the smaller thing. So if we were to print a vector, I'm just going to print a vector of integers, v. So what I'm going to do here is I'm actually going to use a recursive algorithm to print the contents of a vector. I'm going to use some vector function, so hopefully it doesn't throw you off just a whole lot. But the idea here is that I'm going to whittle the vector down. I'm going to print an element of the vector, and then I'm going to recurse on what remains of the vector after printing. So I'm going to print the first element and then recurse for the remaining elements. The stop case will be if I get down to an empty vector. In fact, I should just say if v.empty, return. That's my stop case. I don't want to do a recursive algorithm that's designed to print a vector on an empty vector. So what I expect to happen is the vector is going to get smaller and smaller and smaller and smaller and smaller until it has no more contents. Hopefully that's true in this case, that I can write it, and then it stops. Do nothing when I get whittled down Um, maybe I should draw a picture of this so you can before you see the code, you can see what's in my head by me drawing a picture of it. So let me do that. Here's what I want. I'm going to have a vector just say like 1, 2, 3, 4, 5. So what I'm going to do as an algorithm is I'm going to print the first element, and then I'm going to recurse on the remaining elements. So I'll print the 1, and then I will pass the remainder of the vector back into the function recursively. So the second stack frame will contain this part of the vector. I'll print the first thing, and then I will recurse and pass back in what remains of the vector after that. I'll print the first thing, pass back in what remains, print the first thing, pass back in what remains. And eventually I will get down to where nothing remains, at which point I will unravel the stack. So Magenta asks, am I removing basically the first thing? And the answer is yes. I'm going to print the first thing, and then I'm going to remove it, and then pass the vector back through. Yes. So let's do it. So this is a picture of what it's going to look like. The stack frames are going to stack up in the other order. So we'll start here, and then the stack frames will unravel as we go. And then we'll experiment a little bit just to see something interesting in what you can do with the recursive algorithm if you're clever, which I'm not saying I am, but hopefully you kind of see the point now. So what am I going to do? Well, I'm going to see out v at 0. Yeah, so as each pass a new vector, I'm going to remove the first element from the vector on each pass and then pass the altered vector back through. So yeah, so here I'm going to print the first element, and then I am going to, can vectors pop front? I bet they can. I forget. I don't want subset, I want vector. Here we go. If I can pop the front, I'd be thrilled. No, but I can erase an element. You can only push and pop the back. Oh, it'd be so convenient. Well, I'll erase something. Yeah, so I can erase on an iterator. So what that's going to look like is I will take v dot erase v dot begin. I think that's how I can just erase the first element, and then I will pass it back through. Let's see if that works before I go any further. No. Oh, darn it. Need to be able to use vectors here. No matching for call to erase. What? I just looked at it. I wonder if I say begin +1. This argument is type const vector. Oh, okay. I see the problem. We cannot say const and have this work. All right, fair enough. I got to call it too. All right. Hopefully that's the fix. Yeah, so there's the 1, 2, 3, 4, 5 at the bottom. I should have commented out factorial to get less mess on the screen. Okay, there's the 1, 2, 3, 4, 5. So Yeah, so I couldn't do const on the vector because I actually need to alter the vector by erasing the thing at the beginning every time. So I print the first one and then I erase what remains. Now I'm going to do a little hack here. I'm actually going to print the vector twice. So I'm going to say printing and then I'll put a little thingy in here. And then I will for int I in vector v do cout I. All right, so why am I doing this printing? Because I want you to see the vector whittle itself down over time. So these outputs they take some practice to figure out where and what kind of outputs to do for a recursive algorithm. So how do we know this is a recursive algorithm? Right here, because it calls itself. Here's the stop case. So also it's at least a recursive algorithm that has imagined what the irreducible moment is. And then finally, the algorithm itself is I erase the first thing. I print the first thing. And then I erase the first thing. And then I pass the altered with one less element vector back through. So this will show us what the vector looks like over time. So there's the original 1, 2, 3, 4, 5. And then I take that, I erase the first one. As I'm printing the two. I should have put a new line here. Yeah, I need a new line now. All right, so let me get some chat comments here. So each pass, yeah, so Emberwolf asks, is each pass a new vector? So I think we got that one, but each pass will be the same vector, but with its first element erased. So effectively, every stack frame of the function gets one less of the vector. Okay, so when the function calls itself, does it stop where it was at and start over with the new call? It's stack frames. So basically, the stack frames are all there. In fact, I can do that. We can actually look at that by moving the print statement around. So if we print the array that was being worked on after we recurse, we can kind of see the stack frame backwards, I think. No, it always looks empty. Okay, so that didn't work. My original print was way better. Ah, there we go. That's better. That's kind of what I wanted to. So no, the original stack frame is actually still sitting there, and it can't actually return until the one stacked up on top of it return. Now in this case, each stack frame is not waiting for calculated data on the stack frames above it, but still every call to print vector causes the stack frame to build up, and it can't unravel until we hit this moment, and then the rest of them can all kind of get to there. I can do something with that, by the way. Size, v.size, done. So nothing returns until this last one, but we can actually get this done right here. So we'll put a print statement here so we can see. So wait, why are they always say? Oh, because I'm destroying the array every time. Yeah, I'm destroying the array. That's why that doesn't work. Well, let's make a new one. Now I am going to make a new vector for each pass, so then I can do this. This one's a pain to try to type. In fact, I crashed it from doing that, so I'm not doing any of that stuff. That just makes worse mess than I had before. So yes, this is destructive. This, you are correct, Magenta. Why is it doing that? Allow it. No, it's okay. Oh, there we go. Yeah, so this is destructive of the original vector, and it would be a better algorithm to not do that, to not destroy the vector. There's another way I could do this, but I wanted to make the code easier to understand. So yeah, this one is destructive of the vector. When we're done, the original vector v is completely destroyed. So it would probably be a good idea to make a disposable vector of the original one. Yeah, so that was a good idea. Although that, where's that done coming from? Oh, yeah, I don't need that. So you're right. In this, so I don't want to get too wrapped up in this kind of silly function. I just wanted to do a recursive one, kind of just with a different take. So this one is destructive of whatever vector it receives. So I went ahead and created a disposable one for that purpose. But I wanted you to see kind of how these would unravel. Now I'm going to do something slightly different here. I'm actually going to change this algorithm up. Let me comment these out. So one interesting thing about recursive algorithms is that you can get different behaviors just by changing the order of operations. So if I were to grab that value from the front first, which I could have said, by the way, v.front. So here's a different take. I'm going to get the value, but I'm going to hold off printing the front item until after I've erased and passed back through. No, I wanted a new line. So yeah, so I saw that. Just responding to chat here real quick. So yeah, someone said dummy vector, and and I had to go allow that comment because that's a perfectly useful way to describe the disposable vector that we wanted, a dummy version of the vector that the algorithm can destroy without harming the original. So there's a little bit of chat about that word dummy getting filtered by the Twitter bot. Okay, so I'm going to change this algorithm now. I'm going to go ahead and get the value from the front, but I'm going to do the print vector recursive call before I print the value, just to see what the difference is. Probably some of you can anticipate what happens if I recurse before I print, which is I'm going to see the results in backwards order, which is just really awesome. I've always loved this about recursion. If you hold off on the printing step until after the recursive step, then you can actually kind of experience the stack unraveling itself. So the first element was 1. But the 1 was sitting there waiting to print until all of the stack frames had their chance to print, which didn't happen until this last empty version happened, and then the last stack frame, 5, could actually complete the print, and then the 4 could complete the print, and then the 3, and then the 2, and then the 1. Pretty crazy stuff. Okay, so I'm going to bring up the lab code now so that we can get some hints about that. I can get you going on that before I put a break in and I deal with some project 3 stuff for us, double linked list, so we can go over some of those algorithms. So even if I give you some of the solutions on the lab, the thing to look at, what I would try to do is just kind of develop these algorithms off to the side for the practice, because it really takes a lot of practice to think and implement recursively. But look for the break or the stop case. Look for the recursive call, the function calling itself. Sort of consider the order of operations and try see if you can make sense of the effect of the order of operations in the recursion on the results. So in the example of print vector, if I print the first one before I recurse, then they come out in order. If I print the first one after the recursion, then they end up coming out in backwards order, and that's because of those stack frames piling up and then having to unravel, which is pretty cool in my opinion. Okay, let me make another one and let's go get the lab code. So I'm going to give a fair amount of solution here, which means I'm hesitant to just throw the code up, although I will put a link to the first REPL. But this code I want to leave on the screen because I want people to have to look and think about the code, and at least the process of typing it for yourself. These algorithms aren't long, so this isn't a lot of coding work. They're just complicated because they're recursive. Let me go ahead and get doc test in here because I probably will. Oh wait, that's going to come off the lab. Okay, so there are factorial, you know how to do that. And I will link the other REPL, so that will be there. Fibonacci, the solution is in one of your readings, so I'm going to leave that one be too. Word is palindrome. I'm going to draw a picture of what I want to do with this. But notice that it says I must do it. The whole idea is to try to do these recursively. So let me show you how a palindrome would look if we did it recursively. So let me draw a picture of that. We'll use my current short favorite is Taco Cat, which is the same backwards and forwards. But it turns out that for a computer scientist, there's kind of a more obvious, there's a computable solution here. Backward and forward, yeah, but the one way to compute the solution is to compare the two letters on either end. And if they match, you're in good business. And then what you do is you take off those letters and you compare the two letters at the end. And then you take off those letters and you compare the two letters at the end. If you get to one or nothing, then you have a palindrome. So if you start with anything else, let's go with Taco Cat with a K. So same algorithm. If at any point these don't match, then you know you don't have a palindrome. If you get down to one or empty, because technically this is a palindrome, when you take the two off, you get an empty string. So if you can whittle a string down to empty string or one letter, you have a palindrome. If at some point the two letters on the end don't match, you don't have a palindrome. If you get down to where there's nothing left, that's also a palindrome. So it's all a matter of compare the characters on the end and then repeat the process until there's two break cases here. We get a size of 1 or 0, or the two letters on the end don't match. Okay, so let's do that algorithm for palindrome. So to hopefully make this easier, so let's see, the first is the word .at 0. In fact, I can't do that until so if the word size is less than or equal to 1, then I will return true. Because that should be a palindrome. Okay, so if I don't return true, then what do I need to do? Well, I need to grab the first character and the last character, which is the word .at, the word .size less 1. And then I sort of have two stop cases. So if the first is not equal to the last, then I can return false. That's not a palindrome. And then I have one last thing, which is to return the check on the substring. So I will start at one character over and I will go to size less 1, I think. So I've done these a lot, which is why I can do this. This might not even be correct, but I've written a lot of these. So I have a lot of practice, and that's the way I got to where I can kind of see them in my head better. So if at any point I get down to a word size that's one character or no characters, I'll just call that a palindrome. Okay, so now what's the real work to do? Well, I'm going to grab the character at the beginning, character at the end. If those don't match, then clearly not a palindrome. If they do match, which would be the else part, then I need to repeat the process by checking the next smaller string down, having removed the ends. So the way I did that, I need to do a return because I'm still kind of waiting on my actual result by returning the smaller pieces. I'll take a substring. I will move one character over, and then I think if I back off by 1, I'll be okay. But well, do I have output capability here? I don't. Let's take this and move it into the other. REPL. Okay, let's put it in here. That way we can call it and check it out. So I want to see, what am I testing? Testing word. So I like these output statements, which also takes practice, but they help you get a sense of where am I at in the process. So let's comment these out. And we will try word is palindrome taco cat. I'll set up a little model here. And then we'll try something that isn't. Okay, so we'll try this algorithm out, and we'll also see the print statements to see how they work. My algorithm's wrong. So when it came back through, I hadn't cut off the last character, do you see? Which means I'm not cutting off enough. I need to back off by 2 here. Okay, So now taco cat, which checks out, leads to a coca, which checks out, which leads to coke, which checks out, which leads to the O, which means that yes, it is taco cat, which leads to the coca with the K, which leads to the coke with the K, which does not check out. You can also see where it's short-circuited here at the O and here at the COK, where it found its break case. Okay, so in chat, Emberwolf is asking, what does substring do? So it takes a substring of the string. It takes a subset of the string. So this string word, it takes a substring starting at position 1, which is 1 character from the 0 position, and then this many characters. So for taco cat, if we start at taco cat, we start at the A, and then we take the size of taco cat, which is 7 minus 2, which is 5. So we start at the A and we take 5. So A, C, O, C, A. The remaining 5 gives us a coca for the next call. So this is how I am going from the big to the irreducible moment by using substrings and just kind of cutting down until there's nothing left. Or until I can't cut down because I just realized, oh, this can't be a palindrome. Okay, so there is word in palindrome, and this needs to be fixed with a 2. So these are hard. They take a lot of practice. So I would be as happy for you to kind of see me reason through these and then find my mistake by doing the output statement and fixing it. Let's see, string forwards or backwards. I'm only going to do one of them. So this one is relying on an index. Let's do the start index. So the way this one is designed to work is instead of actually destroying the vector like I was doing before, this one's just going to move an indexing value that we use to kind of only see from the index. This is going to go backwards. So this start index is from wherever on the back end of the array pulling back. So our stop case, maybe I should draw a picture of this as well. I want to leave plenty of time to do project 3 stuff without going 2 hours. So this vector backwards thing, what it does, 2, 3, 4, 5, it actually never alters the vector. I'm trying to figure out the fastest way to draw these pictures, okay, so how is this algorithm going to work if we're going backwards? Well, we're going to be given a start index. So what we're going to do in this case is we're going to print the element at that index, and then we're going to recurse by simply moving the index over. So we're not going to alter the vector, which is why I altered the vector earlier, so just so you saw 2 different looks at this. So the index is going to be the way that we kind of whittle the vector down without whittling it down. So the index, if we started it here, I'd print the 5, and then I'll move the index over. Same vector, different index location. Print, 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 and now the index is going to be at -1, which is stop. So that's how we're going to do this algorithm. What that looks like in code. So if the start index is less than 0, then I got to stop. Although I'm supposed to create a string. How interesting. What do I have for includes here? I do have an O string stream. Very nice. Okay. So I'm going to make myself an O-string stream output. In this case, I'm going to set up in this if else. And then at the end, I'm going to return put string. Okay, so the outer parts is familiar. That this can be done recursively is the weird thing. Okay, so what does this look like? Well, if the start index has become less than 0, nothing. I will do nothing. I have nothing to print. I have nothing to recurse on. I have nothing to add to the string, so just nothing. All right, so if I'm not at the break case, what do I want to do? Well, I want to add onto my output the vector at that start index. And now here's the nasty part. I also want to add after that whatever comes by recursing on it. Separated by single spaces. So that's pretty nasty for a recursive algorithm, but it will help you with the forwards one. I have a feeling this is wrong, by the way. I'm going to go try it out because I have a feeling it is wrong. So let's go put it in the other REPL and try it out. I'm going to need string streams for this, but let's try it out. And then we should be done. All right, so vector backwards as string. That's a nasty old function name. We'll use that same old original vector. So you'll have all this stuff in the samples. Okay, so this one takes some study. If I've gotten to where I move my little marker down to negatives, well, I'm not going to do anything. Otherwise, I'm going to build my output as wherever I'm at, going backwards, followed by a space, followed by whatever comes after me. Not my problem. That's the recursive. Oh, did I comment? Oh, I did. You're right. You're right. Thank you. So thank you, Ember Wolf and Magenta, for having my back. I need this vector back to print it. And I did... yeah, I included SStream, and then I have sort of the catch-all using namespace standard, so that hopefully all that works. Thank you, you guys. It would have. Oh, I still have a mistake. Requires. Oh, dummy. Starting where? Start at the last position that's in the vector itself. Let's see if they come out backwards. It's a string, which won't print unless you print it. 5, 4, 3, 2, 1. That was, in fact, backwards. So this is a trickier one, but the point is to expose you to recursive thinking, to give you some models to do. So this is the solution, and it will be linked. I will link you to this page of notes, which has the factorial, good, and prints out too much junk solution. It has the word is palindrome with too much junk solution. It has vector backwards as string without junk. So that's good. Yeah, so let me switch back over and see if I don't know, sync. That sucks. Oh, it's just start index -1. That's okay. And I didn't get the little space in there. Okay, so recursive thinking. Stop case, or in this case, do nothing case. The recursive case. The order of things matters. So if I put the V start index later, I'd reverse the order basically. So notice on vector forwards string, which I'm going to leave for you to implement, the index in this case is unsigned because I don't need the negative to detect that I'm at the end. What I need about this index to detect the at is if it's reached the same value as the size. So going forward from the start to the end, I don't need signed integer index anymore. All I need to be able to do as a stop case is detect when this index has run past the indexable range of the vector. Otherwise, it's very, very similar. Okay, so I need to put a break in right here so that I can then switch gears. So apologies if you're live streaming and you're sitting here for a long time, but let's take like a 3-minute break. So it's now it's 11:16. So I'll just say 11:19 so that it's 3 minutes and not 5 minutes of sitting there. Water, stretch our legs, and then it's project 3. So huge shift in terms of the brain here after I come back from this short break. Also to put the gap in here so that this part of the video can be more easily targeted for viewing later if people are doing that. All right, project 3 when we come back. Okay, so if you're sticking around, I appreciate it. I know this is a long haul. Okay, so Ember Wolf has a question before I get started. Yes, of course, it's a good, perfect time to ask. So we set the else to move the tails previous, and I did not think that would work past one node. Okay, let's look at that. So that's on push front. So let's have a look and see. Push front. So let's see. New node. I'm drawing a picture. I'm not going to show you me drawing the picture. I'm just going to see if I can find the problem, and then I'll stop and show you the picture where I saw the problem. So next to head. And then if the tail is pointing at nothing, then the tail needs to come here. If the tail's not pointing at nothing, that means that there's someone there. And I need to take the tail's previous and point it at this new one. I missed a step. I can see I missed a step. Good catch. Yeah, you can do that. So it's okay in chat. So Ember Wolf did a this head next previous equals n. As long as there is a head and as long as there is a next from head, that's all okay. You're right, though. If tail... You're right. This doesn't account for everything. Okay, so this does account for nothing, right? Oh, wait. N next equals whatever head is, right? Yeah, so I think you're right that we don't account for every situation. So we need this situation, head and tail or nothing. We need head and tail are 1. And we need head and tail are not the same node. And I think maybe we didn't account for one of these. All right, so let's see if they work for all 3 situations, which I think you are right, Ember Wolf, that they don't. All right, so when empty, so this next equals null, that's fine. Point head at it, that's fine. If tail is null, point at it, else depends. So I think we need to wait on this head equals n. And I'm going to change this to be a head is, yeah, you're right, Ember Wolf. So if the head, so this is the empty situation. So a non-empty situation is going to be 2 different situations. So if head is null, then head and tail are both. Else, I could do it as an else if. You're right, and then we'll have an else. You're exactly right. There's 3 situations that could matter. So this is nobody's home. This one is, there's only 1 node in there, and in that case, then I need to say, I've already pointed this guy. Tail doesn't need to move. So I will say this head equals n. This tail previous equals n. So you're right. You're right, Ember Wolf. We needed to just separate these situations out, or at least I did, to figure it out properly. Tail equals n. Okay. And then if there's 2 or more, so you're right. This is the weird one, which I could have handled all of this in one place, but you are correct. So in this case, we should say this head previous equals n, and then this head equals n. to get that all hooked up. You're exactly right. So tail doesn't need to move in that case. Tail doesn't need to move in that case. Tail does need to move when there was no tail. But if there was a tail on push front, then everybody's okay. So you're right. We should. I found it easier to just. What happens if there's no nodes there? What happens if there's just one, which happens to be both the head and the tail at the same time because there's just one. Move head over, and then I can use tail to point at it. And then if there are two or more in there, then I will move. So I could have said, it's the same difference, isn't it? Yeah, it's the same difference. Let me think about this. Is that true? Yeah. So now I'm seeing that. So now that I see that the else if and the else can be written the same way, then we no longer need the else if. Because they can be written the same way. I think that's the case. Head previous equals the new guy. Yes. Because tail is not even in the mix except for in this one case. Then we don't even need the tail. So, yeah, you're right. Good one. All right, there's push front. Pop front, hopefully I got that right. Already have an empty. So now I'm going to just double check pop front real quick. Next. If I move to null, then make sure that tail also gets nulled out. Okay, I think that one's okay. You can't use clear on pop front. Interesting. I wonder why. I'll try it. So in chat, someone says that when they try to run a clear with this pop front, it doesn't work. If the head's null. All right, so I'm just going to draw a picture on the side real quick. So temp. We already know it's not empty. Temp and head. So this makes sure it's not empty when we try to pop. So we point one at the head. We move the head over, which could become null. And if that's the case, then we make sure and null the tail also. If head doesn't become null, then it's shifted on to another node. In which case we already moved head over, right? Yeah. Delete temp. Knock down the size. That seems okay to me. But do we have pop as a, do we have a pop front? Don't the T's do that? Yeah, T is a pop front. So this may fix the crashing problem. Let me run it. Oh, the delete temp is out of scope? Shouldn't be. No, it's not. The delete temp is in the same scope as the node temp. All right, so I have to, okay, so /main input.txt. So I'm going to put some stuff. Okay, so popping works individually. I'm going to go ahead and add the clear to test this because someone's having an issue with it. Clear is Oh, that's just with the destructor, right? Oh, here's a clear. Clear is X. Okay, so I can implement clear and test that real quick before moving on to new algorithms. So clear is X. I don't have that function yet. I'm going to have to implement it. I also need to look and see. Where did they go? Oh, I had it. I had it pulled up separately. That's it. Okay, so I'm not getting off to the fastest of starts, am I? But I need to know the outputs for a clear. List cleared. Fair enough. List cleared. List cleared. I'm getting oriented here. So list cleared. Okay, that should be all that's required there, and then implementing it. So I shall implement it. I have to compile it. All right, so here we go. Darn it. Oh, but that's fine. I need to do a clearing on it. So I will add values and then clear it. Okay, it doesn't crash. So I think, Ember Wolf, I think that your push front fixed pop front, fixed clearing for me. So thank you for that. I think we're fixed. Okay, so what I wanted to do today was the get and the delete and what else did I have in my get, insert, remove all. Okay, get, that's the easiest one. Get, remove, and remove all. So that's the G, but I'll worry about the get. And let's see what the outputs are supposed to look like for get. There's the G. Value found, value not found. Okay, that's good. Because really it's just looking for a true or false. Can I get that value? Okay, fair enough. So, oh, thanks, Ember Wolf. Yeah. Caught me on the small X, which I think I fixed. So, yeah. Especially when I'm getting warmed up here. So the get wants a value found or value not found. What the get instructions are really telling me is that I just need to return true. I can find a value in my list, or false I can't. So I'm going to make it a bool. Get. It's going to get a T. Why a T? Because we're in a template. All right, so this one's fairly straightforward. I'm going to do it with a, let's say a while loop, I don't know, got false. So can I get it? And I'll say return true, I got it, or false, I didn't got it. I'm going to use a while loop for this. So I'm going to say node star temp equals this head. So I'm going to just start at the head, and I'm going to cycle through the list following the next pointers until I either fall off or find it. So while temp not equal to null pointer, because eventually if we keep moving temp over, it's just going to fall off. While it's not equal to null pointer, I'm going to say if temp value equals the value I'm searching for, then I got it. And I can stop looking. So the break will break the nearest loop. If that doesn't happen, then they need to move temp over. So that one's fairly straightforward, but I need it for a later algorithm, so I did it first. So can I get a value? And I will say got it if I got it. True or false? Hopefully everyone understands why I use true or false here. Because the instructions suggested that I'm really just looking to see, is that value present? Yes, it's found. No, it's not found. So then we will go to our notes. That is a G with a number. So I will go to my input and I will G the 10, and then I will clear it and I will G the 10. So I should get a found, not found. The outputs say value n not found or value n not found. So I'll go to main. I'll do a else if command.at 0 equals the G, big G. Then I will if list get string to integer the command. How did I do that before? Oh, I took the substring 2 characters over because I take the G off, take the space off, everything else is the number. Boy, is that a lot of parentheses. If I can, then I will say cout value. I'm going to change that. Int n equals. We can make this look a lot nicer. And then I can have it for the output as well. List.get n value n found, space in there, else not found. Not found. Let me build it. So I should have a 10 found and a 10 not found at the end. Value 10 found, value 10 not found. All right, so that one's fairly straightforward. All right, so on my agenda, I said after the get, I would do the insert. This one is the nasty one. And this is where my code is no longer going to work because I don't have a pushback. So this is where I can't test anymore without implementing things I don't want to implement. So what are we doing? Insert. And then I'll try to explain insert. So void insert t value. So one thing to understand about this doubly linked list. So we have push front and push back, and we're also going to have an insert that attempts to maintain an ordered list. And where people get confused every semester that I teach this is, well, what if I do push front, push front, push front, and then an insert? Won't it break the ordering of the thing? And the answer is yes, it would break the ordering of the thing. So the design of my doubly linked list is you either do all inserts, which means that it's always sorted, or you do all push back, push front kind of stuff. If you mix push back, which is not sorted, or push front, which is not sorted, with insert. So if you mix calls to pushes and inserts, you are going to get a messed up list. So as sort of the library writer of this doubly linked list, my expectation of my customers will be that they do all inserting or all pushing, and that they don't mix the two. And if they do mix the two, I can't make any guarantees about what's going to happen. So anyway, just keep that in mind. And when we do the testing of your programs next week, we will not mix pushes and inserts. We'll either do a whole series of inserts and then clear the list and then do pushing and popping, or vice versa, but you won't see the mix. So if this insert function is called, we should expect that it was only inserts being used to populate this list at this moment. All right, but that said, let's take care of the easy stuff first. And what I want you to do, you should do this for the rest of the semester, by the way. Look for opportunities to make other functions do their work. So as an example, if insert is called and I have no nodes present, which head being null would tell me that, I don't need to do any algorithm here. All I really have to do is say, hey, I'll push it on the front and that other function will do the job. Simple. I can also say else if the value is less than or equal to the value at the head, then I also don't need any fancy algorithm here. I will just push front. I can also do the same at the other end. So for the insert, 3 of the situations, empty list should go on the front, should go on the back. Those can all be handled by the push front and push back functions. So if I get to here, I already know that I'm going to have to find a location between other nodes in the list for this to work. So this one's kind of crazy because I have to do 2 things. I have to find my spot and then I have to get the node inserted in there. The one thing I know for sure is that I'm going to be inserting between 2 nodes. That's a guarantee because anything on the ends has already been handled. So this algorithm has to find the spot. It has to insert between 2 nodes. So the first thing to do is find my spot. So I'm going to get a temp. I'm going to start it at head. I know I can't run off to the end. And I know I'm not going to be at the beginning because I already dealt with that. So all I have to do is find the spot, and then that spot is either marking where I go after or where I go before. I'm going to draw a picture here in a moment, but I'm going to do I'll do a go after, let's say. Yeah, I'll do a go after. You could do a go before. So while value is greater than temp's value, then I'll just keep moving the temp over. So I'm going to draw a picture right here on that part of the algorithm, just finding my spot. So let's see what that looks like, finding my spot. So I already know doesn't really matter head or tail because I've already dealt with that. I already know. So if I have the value 15, let's say, so let's just say I start temp here. And I say while this is greater than what's at temp, move temp over. So it's greater than 10, so I will move temp to here. I'm going to mark it with a pencil. And then in this case, temp is going to stop there. So what I know is this new node has to hook up in between here. It has to hook its arms up here and here. And these arms have to hook up to it. So this is where temp will stop in my current algorithm. And this is an N, which I forgot to make. Let me go make it real quick. Oh, I'll just make it here. Okay, so there's my N that I just drew a picture of. Okay, so here's my N. I got to hook it up all in here. So I say from experience that it works best for me if I always, always, always connect the new stuff first. So I need to connect this here and this here. So this is N previous. This is N next. So I need to hook those two things up. So I need to do an N previous somewhere and an N next somewhere. I wanted to do that. That's fine. That's fine. So where does the N next go? N next goes to the same place as temp. So N's, oh, I have these backwards because I'm dumb. N next, previous. N next goes to where temp is. So it's just temp. N previous goes to where temp's previous goes. So N next, N previous goes to where temp's previous is. N next goes to where temp is. So that's the new guy hooked up. Now I can do the stuff that's already in there. So that's this problem. Now this guy's all hooked up. Now I got to move these things around. This one, Ember Wolf already has experience about this. This one is the nasty one because there's no direct way to get to it. This one is not so bad. So this is a previous. So this is temp's previous, and I got to move it. So I need to move temp's previous, which will be to N. So if I take temp's previous and move it to N, that's good. Now I got to get to here, and I just cut off previous. So I'm going to have to go N previous next. Or I change the order of things and I put this off so I can go temp previous next. It doesn't really matter. Either way, I'm 2 steps away. So N previous gets me here, and then next gets me this. And I have to take this and point it at N. So it looks very circular and strange. But if I go N and I take what's now its previous, which is the neighbor on its left, and then I take its next and make N its new neighbor on its right. Pretty crazy. Which is, so N previous, next, reroute that to go back to N. So now I have N hooked up wherever it should be. And I can finally increment the size. One thing to be careful of here in the code, notice that I do all of that work, including the size in the else part. Why am I being careful about this size? Because pushback will increase the size. Push front will increase the size. Push front will increase the size. So when those are called, I need to let them handle increasing the size. It's only in this else part where I have to deal with the problem of increasing the size myself. Hopefully this is correct. I don't have a good way to test it right now because I don't have a push back for myself. Hopefully this is correct. If not, we will find out and share our solutions together on Piazza. Okay, but that's pretty close, reasoned out. All right, there's insert. Now remove. That's a nasty one. Insert, by the way, is automatic. There's no fail to insert. It just inserts, and if there's duplicates, that's fine. So now remove. Let me go look at the required output. So insert. Yeah, just say value in inserted. So there's no possibility of failure there. Remove. Okay, so remove can fail because it's possible that you don't find the value you're trying to remove. So in that case, we need to design a remove that signals success or failure. So I'll return a bool on a success and a false on a failure. So remove t value. And the other thing I will note about it is, I think I saw this in these notes, remove the first occurrence. So all I have to do is look for and remove the first one. I don't have to look for all of them. That's someone else's problem because there can be duplicates. Okay, so remove. I'm going to go through the same process as I just did. Well, if there's no nodes, then there's nothing to remove, so I will simply return false. Else, if the value I want to remove matches the value in the head node, well, I can simply do a pop front, being careful to still return true because I succeeded in removing it. Pop front doesn't have a true or false on it. It has an exception, but internally I know at this point that I have a node there, but I need to be careful that I return true because I will succeed in removing one. Same goes if the value is at the tail, then I can simply pop the back and return true because that's a successful go. Else is the nasty one. Because else means that I am removing something that's in between other things. Kind of like insert, where I'm inserting something between other things. By process of elimination, this else part is removing something from in between two other things, which means unpleasantness. So let's find our spot. I already know that all I have to worry about is finding my spot because I handled every other eventuality with that logic. So all I have to do is find my spot and then do the work. So while the node that I'm looking at does not have a value that I want, I'm going to keep marching along. And then I'll go draw a picture here so you can see what I mean. I think I can finish here in the next few minutes. And if you're bearing it out, thank you for that. It's okay if you got it. Okay, so I already know that it's a node between two others. So if I want to remove 10, I already checked the ends. I checked for empty. So all I have to do is know that my temp pointer is going to be sitting right here. So that's all fine and good, except for I got to do some rerouting of the neighbors. So I have to move this one over. And I have to move this one over. It doesn't matter about these that are associated with temp because I'm going to delete that node anyway. It's the ones on the neighbors that have to be rerouted that matter. And because temp is sitting here, getting to them is a pain. So I'm going to have to use temp to get to the previous one to move its next. I'm going to have to use temp to get to the next one to move its previous. It's crazy stuff. So in code, once I know my spot, then I will use temp to get to the next one to move its previous to something. Then I will use temp to get to the previous one to move its next to something. And then the whole matter is what goes here and here. So if I use temp to get to the previous, to reset its next, it's going to be pointing at temp's next. And then if I go temp to get to its next, to reroute its previous, it will be temp's previous. So the previous goes to the previous and the next goes to the next, if I remember that right. So just whatever used to be gets rerouted. Yeah. So Emberwolf says the tail is technically the last occurrence. That's true. But that's already being, that'll be dealt with by pop back anyway. So I'm not going to worry. This is just removing one. Oh, sorry. Yeah, sorry. I just switched over. So we've already dealt with the eventualities that we're trying to remove from an empty list that can't succeed. Or the value we want to remove is in the head node, then we can just pop front and return true. Or the value we want, oh shoot, is in the tail node, in which case we can pop back and return true. So if we get to this else part, the only other possibility is that we need to get a node that's in between two other things. So this should accomplish the routing. I'm going to go back to my paper and double check. So this previous next, or temp previous next equals temp next. Temp next previous equals temp previous. That gets everybody's arms moved around, and now I can take temp out. Now temp can go. And in this one case only, I bump down the size. Be careful about that size counter, because you should only do that in this function in the one case that you have to manually code. So there's a remove. Hopefully it was all showing for long enough on the screen that you can get it. And remember, you can always go back to the break in the video to find that. The last one, if there are multiple values that are equal to the tail node, the else will mess up. No, it won't. So the question is, what if there are like 6 20s at the end of the list? Will that get messed up? No. This remove will only just find the first one and remove it. So it's just going to remove the one. It'll leave all the others. It's fine. Now we are required, if I look at the notes, we have a eliminate all occurrences. So we have another function whose job it is to look through the list and get rid of all occurrences of a value, which it turns out is an easy one to do. So the one we just did is just find the first one and remove it. If there's others, that's okay. So let's do that one, which is very easy. So removing all, what is the output supposed to look like? Remove all. Yeah, so this one's tricky because we're supposed to also keep track of whether or not we could remove any, one or more. So we're going to have to be careful about that. So I'll put it up here. So still also use a bool, remove all of this value. So I'm going to do it this way. I'm going to assume that I remove none, and then I'm going to keep count of how many I remove. So while this get value, and I'm going to use my other functions. While this get this value, I'm going to this remove the value. So I'm just going to loop and remove one at a time using my remove function until they're all gone. And then I will just add to the count. Because this function is supposed to signal whether or not it achieved even removing one, much less many. So I'll just keep count. I'll know if none were removed or if several were removed. So I'm going to leverage my get function to know if there's still more there, and my remove function to get rid of one at a time until I can get no more. And then I will count how many I have removed. So at the end I can say if I removed more than none, I'll return true. Otherwise, I'll return false. And then my main can say, if remove all equals true, value n eliminated. Else, if remove all equals false, value n never found, not found. So that one's relatively easy to do, except for the trick of how do I know whether or not I actually achieved, I succeeded in removing one or none. Well, I'll just keep count so that I know once I'm done with my loop. If I remove more than 0, then yes, I found it and eliminated it. If I removed 0, then I never found it. It's how I would do it. Okay, I think that's where I need to stop. That's 2 hours dead on. So I hope that's everything that you need. These last few were not tested, so I hope that there's no bugs in them. If there are, let's get on Piazza together and remove the bugs. Otherwise, I hope that you kind of know well where you're going here. I've mostly left pushback, pop back for your work. Thank you, group today, for helping me debug push front, which was a problem. And to string, I think I'd never eliminated, I never implemented. Yeah, I never did a to string thing. Otherwise, I hope I left it on the screen enough for you to study. So I'm done. I'm going to do 10 or 15 seconds on what I worked on today. So I'm going to go to the top and I'm going to shut up and I'm just going to put my functions on the screen. Here at the end, something is wrong. Okay, so here we go. If I can get, yeah, so there's the new insert function. I'll leave it there for a few seconds so you can see it on the video later. There's remove all. Here is remove. Here is the fixed push front. Thank you again for finding that bug and bringing it to our attention with the fix. Awesome. I did not implement a pushback. That's for you. It's not as easy as that sounds, by the way, because you just think, oh, I'll just flip all the heads to tails and it'll work itself out. Probably, but be careful. Draw pictures. Pop front. Get. All right, so hopefully that gives you all the power that you, oh, there's my clear that I implemented today, which I did a minimal test on. Hopefully it works with the fixed push front, which is, I think, where the problem was. All right, that's it. Got to run. Anyway, hopefully I've left you with plenty enough to do the project. If you're just seeing this for the first time, then skip forward to the break in the video from last week, week 12, and you will find in there the beginning discussion of this doubly linked list. So yes, so for those of you who have any remaining questions, of course, office hours is open this week as always. The drop-in time, the scheduled time, Canvas inbox, Piazza. So yes, please do make use of all of those channels, and I'm happy to answer more questions about this project or anything else that you have. So have a great week. Thanks for sticking out this long if you were able to do so. Sorry it's been taking so long. We might get more control over our timing now that I know that you're getting a little bit more familiar with the pointer syntax. We can maybe be a little bit more efficient, but I just felt like I got to spend the time that it needs, and I hope that that's not kind of wrecking your day for me to do it. Okay, I'm going to run. I will see you, if not sooner, during office hours. Then I will see you on Monday morning, late Monday morning next week. So take care. Have a good run on the project. Let me know if you have issues. Let Piazza know. Drop in during office hours or scheduled time, and we will help. So see everybody later.